Perfect.
Okay,
Alrighty.
go ahead and start, folks. Thank you for taking time out of your busy schedule. Andrew's a great supporter of ALTA, and he's agreed to give us a presentation on PK maintenance applications. So I'll turn it over to him.
Thanks, Gary. Thanks for having me, and thanks all for making it. I know, as Gary was saying, it's pretty busy with planters rolling, and yeah, thanks for making time. So, for those that didn't catch the bit of discussion just now, this is more of a brainstorm, a bit of a provocative title, but it's meant to instigate some, I think, debate whether we should rethink P&K maintenance applications. And I'm not saying we stop soil testing, not at all. I'm saying whether we should be adding to our P&K fertility programs grain testing in order to inform more accurate removal rates. And as I'll point out, the foundation of whether you're in a build, a drawdown, a maintenance approach, it's all predicated on how much P&K is coming off with every bushel. So if you have uncertainty or inaccuracy introduced in that stage, it just throughout the whole rest of the calculations, there is augmentation of that uncertainty. So with that, I'm going to jump into this. If there's any really burning questions, I'm more than happy to stop and discuss. So this work is a result of myself and Luke Bergschneider, who's on the call, our lab's on-farm research specialist, and it's the result of some field sites from his master's work that we're now trying to build on. So, first, I want to say that this is part of our program and it's funded in part by Illinois NREC, great supporter of research in the state of Illinois, as well as this National Science Foundation Center out of North Carolina that supports basic research on all things phosphorus. And then the Farm Bureau. As you'll see, we did this work in very close collaboration with Bureau County Farm Bureau, BCFB, up in north central state. So these are the sites where we work across Illinois. The ones in yellow are the ones that we'll focus on today. We're drawing from these on-farm locations to address this question of should we be rethinking how we calculate the maintenance rates for P and K for corn and soybean, which is really a question of how much P and K is in every bushel. So this came out from Farm Doc from the U of I just yesterday, Monday morning. It struck me because it's one more projection of not a great year in terms of net returns to agriculture in the state. If you focus here on soil fertility, the costs are different by crop and by region of the states. But if you compare those costs, we're talking around 200 for corn, around 60 for soybean per acre. And depending on whether you own land or not, or what your land costs are, the total cost per bushel produced is currently based on these estimates above the cost of production. So production at a loss. Now, if there's room to wiggle on the soil fertility inputs, other inputs are an option, then that might be enough to begin to close this gap. So this then is the question that motivates the work you're about to hear, which is where can I cut back? We've heard this question probably 3 times a week now since November from farmers across Illinois, and I'm sure from your other states as well. And this is a tough question to answer because you can't really change land costs, right? The landlord is going to charge what they're going to charge. Some costs like buildings are fixed, etc. If you cut back on seed, that can be a big issue for yield. So this really gets tricky, and people often center the question on nutrients and not really nitrogen for corn, but for P and K. So I'll say right now that I'm not going to talk today about soil test-based approaches. I think we're all aware that if you've got a melic P that's above 80 ppm, you probably have no business economically putting on P, right? That's pretty common sense. We're not talking about those obvious, yes, you should probably, sorry, that yes, you can skip a year or two of application if you have very high soil test P and K levels. We're talking more in the realm where someone wants to cut back on P and K. They're on the border of responsiveness, and perhaps they're above that, but they're not sure how to do it safely. Meaning, is there a risk of a yield drag that is a missed dollar per acre net return? So where can I cut back? I think we often have very repeated answers, right? Look at your soil tests. Great. Farmers, I think, are well aware of this. I want to propose that we've not thought this deeply when it comes to the offtake rates. So some background here. Grain and P grain P and K central to drawdown, meaning how much P and K is coming off with the bushels is essential. If you think about this figure from the Ohio State, at all steps, there's this essential understanding of how much is removed. To put it differently here, we can think about this as a simple balance, right? We've got inputs. This is pretty simple. It's fertilizer, it's manure, that's a bit more complex. Then you've got outputs, which for most systems in the corn belt are going to be grain. Silage as well would qualify. And these are the major input and output fluxes or transfer of mass in most cropping systems. To make this even more simple, depending on the strategy that you're targeting, are you trying to build, maintain, or draw down based on your soil tests? There's different ways to think about the flows. To put it simply, when you're building, the inputs exceed the outputs. When you're maintaining, they're equal. When you're drawing down, inputs are less than the outputs. How much less is a lot like building. It's about how quick do you want to get there. If you want to build very quick, you put on a lot more. If you want to draw down very quickly, you put on nothing. And now that's the fastest drawdown rate possible. To put this from balance terms, like a bank account, positive balance is building, maintain is neutral, and drawdown is negative. Okay, but all of these are based on knowing the real value of the output. The input is easy, especially in non-manured systems. It's just the fertilizer, the potash, the DAP. But what about the output? And this really is a question about the grain or silage, if we're doing that, or forage, as we just heard, might be high priced. This, I think, is where we've missed an opportunity of we're using a constant fixed value. It's even called a coefficient, but there's variability around that average. And there's an opportunity there to cut back on application rates in some cases to save dollars with no compromising of soil fertility or of yields. That's the pitch that I want to make here. So, a bit of background. I like to go back to our predecessors. They figured out harder problems with lesser tools than us. And one of my favorite predecessors on campus of the U of I is Dr. Cyril Hopkins, who did his PhD while he was at U of I, but it was mentored by Cornell professors, as you can see from this left-hand image. His PhD dissertation in 1898 was the chemistry of the corn kernel. And what Hopkins studied basically was the composition, fiber, sugars, protein, fats, but also there's a little bit here about nutrients. So this is the beginning of this idea that, well, when we harvest biomass, there's nutrients in the biomass, we have to replace that. And the way that they thought about this was the productive capacity. Hopkins literally writes about in the second bottom left snapshot from his writings in 1908. He literally writes about how many crops worth, meaning how many offtake amounts there are of P and K in the soil. So they're very much thinking about if my soil P and K stock is X amount pounds per acre, how many corn crops of offtake is that equivalent to? So this then I think is the genesis of what we could maybe say evolves into the nutrient offtake concept. Again, this is 1908, a full decade after he finishes his PhD. On the above table up here that is just looking at the N2, sorry, the K2O, the P2O5 content of corn. At the time, the Germans were leading, as you can see from these names, and yes, that's the same Liebig as the Liebig law, really the Sprengel-Liebig law, but that's the same Liebig from 1830, 1840 that he's responding to half a century later in his PhD work. Alrighty. So Hopkins figures out, by the way, in 1908, the harvest index is he thinks it's about 74%, and these are open pollinated, hill planted corn. And he gets pretty close to what we think it is today. And these are averages, of course, but I think that's impressive. For the P content of corn and thus the removal rates, he's pretty close if you believe the current Illinois agronomy handbook value, which I'm here to point out works, but we can do better at the field scale. We can do a lot better, in fact. Okay, so this brings me then to these handbook values. These are like critical values for soil tests. They're averages, not literally sometimes, but they're trying to represent, by and large, a reasonable value. That's important. It made agronomy advance to where we are now. I do not think it's going to get us to the future. What is the future? More judicious, economically speaking, use of P and K in a way that pays for itself. Yes, we have the tools for that, but admittedly, I think they're not going to bring us to that next level. Something like VRT, 2 acre grid based management of P and K. So, if we look at common land grant recommendations in the Corn Belt shown here for corn and soybean, just to focus on phosphorus for now, there's some variability here across states, which is not unlike the motivation for the FRST effort, which is trying to harmonize critical values across states. Because just like soil test critical values, these removal rates should be similar across state lines. They probably will reflect the agricultural cropping system conditions, soil type, probably hybrids for grain, things of that nature. So the first point to make here is that these are all ballpark similar. We're seeing values for P for corn to range from 0.32 from Iowa to 0.37. And Illinois used the 75th percentile, by the way, not the 50th. If we use the 50th, there's even more agreement with other states, the tri-states with Iowa. Michigan's coming in a little bit low here, but they're using the median value. You get the idea, right? We're plus or minus 0.05 pound of P2O5 per bushel of corn in these examples, which isn't bad, but this is the beginning of, well, what if we get the exact value? Could that be a way to avoid applying more than what we need, whether or not we're doing drawdown, build, or maintenance? Okay. So, as a side note, since there's a very brainy crowd here, I do think it's worth pointing out this whole P2O5 and K2O. It's good that we recognize that it's not real. I mentioned Hopkins that was following half a century after Liebig, thought to be from the Liebig law of the minimum, the father of fertility. These aren't real, and these are archaic designations that we somehow are still using in the fertilizer and soil testing world, kind of like pounds per acre on a soil test that I don't think have any place. There's my contentious, provocative statement of the talk today. There are some good papers that I'd recommend that you check out. Hans Lambers and Jim Barrow went on the warpath about 4 years ago and published basically the same paper 4 times in different journals, so everybody saw this. Um, it's a really interesting take, and what they point out, they did their homework, is that if we go back to the 1820s and 30s, Sprengel and Liebig, they thought P2O5 and K2O were real because of someone named Berzelius in 1814. Not Brazil, Berzelius, excuse me. But basically, we're using chemistry terms when people had no idea what P and K were like in soils. And when I say what they were like, I'm talking about the chemical, the compound. So it's good to point out that I'm using P2O5 and K2O because that's what the states are using, but these aren't real. These aren't real molecules. They don't exist in nature anywhere. They're simply designations. Alrighty, hopefully that was a fun fact of the day for you. So going back to here, if we will forgive the sin of using archaic denominations from the 1814 period, this is what we think of as P2O5, K2O offtakes. Now, that's in general. I want to now talk about how these are averages and beware of the average if there's a distribution. The fatter the distribution around the mean, the more caution is warranted. The more narrow, I think, then the more useful that the mean is going to be. This is true of critical values on soil tests. It's true of grain P and K values. So this is some nice data that was produced by Dr. Steve Coleman from the Ohio States across the tri-states. And it points out that in general, when there's more yield, there's more P and K. This seems obvious to us, but there's some value in looking at the variability at a given yield level. So if we're looking at 200 bushel corn or 60-ish bushel soybean or 100 bushel wheat, these are the red arrows. There's a lot of variation. And when I say a lot, I'm talking about the offtake amount can be as high as, 40-ish pounds of P2O5. That is not the right unit, folks. That should be pounds of P2O5 per acre, not per bushel. My apologies. And it can be as low as around just under 20 or so. So that's a 2x range for 200 bushel corn. We see a similar, in fact, a larger one of 2.5x for soybean, and then a similar range of 2.5x for wheat. Again, apologies. This is pounds of P2O5 per acre, not per bushel. The point then is that that is substantial variability. So what if you're pulling off soybeans that have higher P2O5 or lower P2O5? are you under or are you over applying if you're using the handbook value, the single value, to guide your removal calculations? If we look a little bit more at the concentrations of P and K within the bushels, this is the same data set shown differently. So we've got on the y-axis the yield as we saw last time, but now we see, sorry, on the x-axis, on the y-axis, we see the concentration. And this is now elemental because that's how we get it back from the testing lab ICP. And the point here that I want to make is that concentrations, they don't really vary strongly with yield. We don't see a clear increase in concentration with yield. That would be kind of weird, or a large decrease. They're basically flat. This also, I think, better showcases the variability shown here with these red lines for a given yield, the concentration varying. So because concentration varies at a given yield, really across any yield level, we then get the removal rates pound per acre different. So for the purpose of this talk, I'm going to use removal rate as a pound per acre takeoff. I'm going to use concentration as a pound per bushel. That's how I'm going to use those two terms. Okay, here's what I mean by beware of the averages. I think you've gotten a flavor for this, and this data in front of you from Illinois, I think something like 7,000 grain samples sampled across the states in 2018 by doctors Villamil and Nafziger. This gives you, I think, a more explicit idea of distributions and why they matter. So let's begin with the one for K. We've got here the K concentrations for three major crops of Illinois, shown by color, and look at for corn for the K values, just how narrow that is. That's a good thing when it comes to using a handbook value. If the population, to use the stats term, so if all the bushels of corn across the state are pretty tightly around that mean value, we can use the handbook value with really high confidence that we're not under or over the actual offtake of the field. If we're looking at soybean, though, it's a lot broader. If we look at phosphorus, it's overall pretty broad and exhibits a similar broadness as what we see for K for soybean. So already we can hypothesize that, well, maybe there's more inaccuracy in the handbook guided removal calculations for P as a nutrient. And when it comes to K, probably more so for soybean than for corn. I hope that makes sense. It's based on these distributions. In an ideal world, all of these distributions look like the K for the corn here in pink, nice and tight, minimal variation. Okay. So then if we think about how we use these values, these handbook values that you saw a few slides back, they're using typically the median, sometimes the 50th percentile as the average. These should be about similar. Averages beat guesses, but as I've been harping on, we can also have false confidence. I hear a lot of farmers say, well, that's the handbook value, as if it were set in stone. And I think this is where the land grant needs to do maybe a bit more transparency in its communication of this is how the sausage gets made. These are, in fact, distributions. Average, again, beats nothing. It got us here, but it's not going to take us there where we need to be more efficient because of that uncertainty. So 50th percentile would look something like this. In some states, like in Illinois, we use the 75th percentile. The idea is that it's safe, so you avoid so that you have fewer cases of under applying for a maintenance-based calculation. But that means that in 3 out of 4 fields, you're over applying. Let that sink in. You're over applying in 3 of 4 fields by using the 75th percentile. If you use the 50th, which is probably more defensible, still half your fields are over and half are under on the maintenance calculation. Why this matters is that do this for many, many years, and you can either be mining or you can be building up nutrients, which in some cases, besides the loss of dollars, didn't make sense to apply, it could lead to water quality issues. So here's an example to make this more concrete. For 200 bushel corn, if we think about what this looks like for phosphorus, there are some fields that if they're right on the middle, you are that lucky field that is the 50th percentile. With that kind of yield, you're taking off this much pound of P per acre. And this is an elemental, not in P205. Sorry. If we go down to the lower percentile, this is the bottom 10%, the lowest 10%, we're 10 pounds under, right? So that would be something like 22 pounds of P205 per acre difference from the average. And vice versa, if we go to the top 10%, we get a little bit more than 10 pounds. Now, between these extremes, that's about a 44 pound of P2O5 per acre difference from the bottom 10% to the top 10%. And from the average, these are both about 22 pounds of P2O5, 10 pounds of P. That matters when DAP is costing what it costs and when grain is worth what it's worth today. Same goes for soybeans. This is what I mean by there's an overlooked opportunity to try to dial in the exact calculation on what in that field is coming off with every bushel. Okay, so I want to put some teeth into this and make it more concrete by going on farm. For this, we're going to go to the central north, northwest, arguably, part of Illinois. This is just north of LaSalle, Peru, off of Route 80. So we're talking an hour-ish, hour 20 west of Chicago. This is Bureau County as well as Henry and Lee County, where we've been working with a group of fantastic farmers. Three of them are featured in this piece from the Furrow magazine. We've been working with them for upwards of 6 years now, and we have lots of different studies as part of our management program, from nutrient losses to balances of nutrients. And we've included in that program, how do you understand the true maintenance rate to better manage nutrients? Whether you're doing drawdown, whether you're doing buildup, you still need to know the exact offtake. So a bit more about these sites. We are across two major watersheds. That was the origin of the work. Now it's just all things fertility and water quality. Three counties, as you can see from this bottom left map here, largely in Bureau County, just north of Princeton. We've got currently 12 farmers. It might be 13 now, I think, with one that just signed on. 23 fields, largely corn, soybean. We've got a couple of corn on corn sites. And the amount of monitored acres that we look at for all these different parameters, over 1,200 acres. So we're trying to go at scale here. These are not small plots. These are real, and these are commercial fields. Now we've sampled these in a 4 acre grid. I say we, it was Luke and the other techs that were doing this hard work. And we realized that we had a nice data set to test this question of does looking at the grain P and K offer any cost savings by virtue of better dialing in the maintenance rate. So this work was funded by NREC and IFB, and here are the results. So I'm showing you here the results over 2 years. You're going to see a few graphs. And before we dive into the specifics of corn P, the way to read these is we've got the number of grid points, again, on a 4 acre grid over 2 years, 22 and 23. We've got the pounds of P per bushel here as a difference in the handbook relative to what we measured. So because we subtract the measured from the assumed, the handbook value, if you're to the right hand of this black bar, it means that we added more than what we needed, meaning that we overestimated the nutrients in that bushel of that grain crop. Okay? So these are not absolute pounds of P2O5 per bushel. This is the difference. So in this example, most of the corn that we measured over these 2 years across all these fields, they had less P than what the handbook said it should. And as a result, we're on the positive, right? We have a positive difference. And then there's a whopping total of 4 fields where we were at or under the handbook value. Okay, so that's how we read this. Then the average is shown here by the pink for the year and by the blue just to look at whether this differed by the year. And the answer is yes, it does slightly. So if we sit back here and look at this is corn phosphorus, what we find is that for the majority of fields, we're talking like 97% of all of the grid points within these fields when they were in the corn phase, whether it's corn, soybean, corn on corn, we find that we're overestimating the offtake rates. And specifically the amount of P2O5 per bushel, we're overestimating it on average by about 0.07 to about 0.1 pound of P2O5 per bushel. Now remember, the state rec for Illinois for corn is 0.37. So an average of 0.1, that's a third. We're 36% under the handbook value. So that means that we're overapplying in that magnitude. This is where the cost savings start to come in. So this is corn and phosphorus. If we now change and we look at corn potassium, Here we again have that black line. If we're to the right, it means that we have a higher handbook value assumed than what we're measuring for K2O per bushel. This is the difference. And we see that it's not as severe in magnitude. So now we're averaging under 0.04. We're really averaging more like 0.02, 0.03 pound of K2O per bushel. So that's 3 times lower amount than for P2O5. But overall, in terms of are we above? Yeah, like we saw for P, for corn K, we're still overestimating in 95% of all the grid points on our 4 acre grids of these acres, the amount of K coming off with every corn bushel. Again, a place for savings. Now, there's less amount of K2O being overestimated, so not as much savings potential if we use the measured, not the assumed handbook rate. Now let's switch to soybean. Same basic idea. You've got as your North Star that black bar, too little added or too much relative to the handbook value versus the measured. And we see here that for soybean phosphorus, it's now there's more of a left-hand shift. We now have more fields that are actually not getting enough P if we're doing the handbook value compared to what we were to measure. But we still see this theme that there's more P2O5 per bushel assumed in the handbook than what we're measuring in these fields. The magnitudes are a little bit lower than for corn. We're now still 0.05 to zero point 0.1. Note that there's a wider distribution though for soybean than for corn. We're getting up to almost zero point 0.2 pound of P2O5 per bushel over using the handbook than if we were to measure that grain at these grid points. Okay, soybean K, this is the most interesting one. Remember in that graph of the distributions that soybean K was much wider than a corn K? Well, it turns out that for these fields and these years in Bureau, Lee, and Henry County, the handbook value is pretty much spot on. In fact, it's a little bit of an underestimate as an average across all of our grid points if we ignore what's happening out with this outlier. I suspect there might be some issue of the yield was very low. There may have been over concentration in that grid point, and you can get these artificially high concentrations with very low yields. Or maybe that was just a lab error analysis. But here, the point is that in this example, for these fields, the handbook value is spot on. That's a good thing. Now, there might still be some value in grain testing because half of the grid points were higher by the handbook and half were lower. So if you're trying to do a build, then using the handbook was insufficient to inform the build. It may just be a maintenance in that example. And if you're trying to do, say, a maintenance, then you're probably doing a build if you're using the handbook value for these fields. Alrighty. So let's talk about the economics here, because I think this is not, I think this is the motivation for the work that we're doing in this and other locations, and it's why we have this webinar in the first place. So to think about this, a couple of assumptions. First, it's the same data that you just saw. We're now translating the cost per acre, assuming 860 per ton of DAP and 505 per ton of potash. And again, we are doing the difference dollar per acre of if we had used the handbook relative to what we know to be true because we measured the grain and that's the actual offtakes. Okay, so if we're trying to apply a true maintenance, the neutral balance, this is the difference in what we would be spending. Either we're underspending or we're overspending. And I'm going to use that term here. It's not over application in this example. We're overspending relative to the maintenance cost. So we've got corn on left, soybean on right. To walk through here with corn first, the red box is where we are over in terms of dollars spent for maintenance that weren't needed because the amount of nutrient was more. This is the example of P that I'll be using here. So this is important because it means that for basically all but two of our grid points, so this is something like 98% of all of the corn measurements we did in these fields, for almost all of the corn points, A farmer making a maintenance application is spending dollars that they do not need for a maintenance P application. And that average value, similar by year, is about 20 to 22 bucks per acre. That said, we have a chunk of points, 10% of grid points, where they overspent by 40 to almost $60 per acre based on current DAP prices. Not a great deal. If we go back to the farm doc, that's over a third of their fertility budget for the entire year that we just threw away on unnecessary maintenance. To put it differently, these fields are doing a build application for P when they think they're doing a maintenance. And this is not a good year to do build applications just because of the costs. So for corn, for phosphorus, a very, very clear picture of this is appreciable. 20 bucks on average per acre, up to 59 bucks per acre. That might be the margin for a lot of guys this year. So we have clear overspending. For soybean, again for phosphorus, as this example, we have less overspending. Now it's about 80–85% of all the grid points overspent. We see a similar minor fluctuation by year by the two colors and the dotted lines going up. But the point here, as I was saying earlier, because there's less overall magnitude of the overestimation of P per bushel with the handbook value compared to what's measured, the savings, or let's say the overspending, excuse me, thus the savings potential are a lot more muted. We're talking an average of 1 to 350, or rounded up to 4 bucks per acre. And there's more of a spread here, but we're still not even cracking 15 or 16 bucks per acre, worst case. Most of our fields in soybean are overspending by less than $10 per acre. Again, the average for corn was 21 bucks across the 2 years, as high as 59. So if there's a lesson here, it's that for these fields, at least, bigger savings on corn for measuring grain P for maintenance, less savings, but still appreciable for P. For soybean, excuse me. Now, K, we don't have the slides here because, well, time is the major reason, but this gives you a flavor. And also because, again, P was more overestimated by the handbook than measured, so the savings will be much greater for phosphorus. Now, if you begin to bundle this, right, P and K, corn and soybean, these total savings on a 2 year rotation for P and K programming of fertility, we now might be in the territory on average of 30 bucks per acre. And in some of these high overspending examples, we might be in a territory of 65, 75 bucks per acre for maintenance. This is a prime example of, I think we've overlooked this for some places as a savings. So let's talk about why. Why is this happening? Are there any insights that might explain the variability in this? And is this spatially explicit? What I'm thinking here is about VRT. I would contend that VRT might be as benefited by grain sampling as it would by soil testing. We pull soils on a 5 acre grid for VRT, sometimes a 2 acre grid. Why not do grain sampling on a grid for VRT, especially if you're doing maintenance VRT? The logistics aside, we'll talk about that of how do you pull soybean grain samples on a grid. That sounds like a nightmare. There's potential here. So we've got here one field, corn, soybean. It was in corn in 22, soybean in 23. Again, these points are roughly on a 4 acre grid to give you a feel of the scale. Sorry, yeah, a feel of the scale of the field. And you've got here the absolute content, the pounds of P25 per bushel of corn and soybean. Lighter color means a higher concentration. Note that the scale for corn doesn't even get up to the 0.37 that is assumed by the handbook. They're all under that, consistent with those values being a third under the handbook across all these fields. So if we look at whether there's any correspondence of P2O5 per bushel for corn and soybean, do we see the darker, so the lower content in the same spots from the corn to the soybean? There's not a whole lot going on here. There's no pattern that slaps me across the face when I look at this. If we now look at, in the case here for soil test p-values, this is melic phosphorus by ICP, compare it with the removal rates, and then by the same 2 years, the same exact field, the same grid points, there's no clear correspondence. So the way to read this is that a bigger circle or a bigger triangle means there's more removal, now pounds per acre. So this circle here being larger means more came off. If it's smaller, like down here, less came off. total pounds per acre. You've got corn in circles in 22, as we just saw, soybean in triangles in 23. And now the colors signify soil test P. So we've got some pretty high levels, ppm up to 80, and some lower levels that you might expect a yield response, whether it's economic is a different question of, around 20 or sub 20. And if we look at the size of the symbol with the coloration, you might think, well, maybe as there's higher soil test P as we go from yellow to red, there's going to be more removal if there's luxury consumption. We don't really see that here. So there's not a clear link. This is one field though. So if we look at all the fields across all of the grid points from all the years we have, just a really simple, intentionally naive univariate analysis. We find that there's very little variation in the grain content, so the pounds of P2O5 per bushel of grain for corn and soybean, and same for K2O as a function of the soil test for P and for K. Not that we really expected it, but it's good to check out. So to put it differently, about 13% of the variability in the corn P2O5 content can be explained by the soil P test. It's not nothing. And it might point to, well, maybe soil test values along with other things like the hybrid being used, other soil properties, maybe these together in a multivariate approach could maybe be useful for predictive mapping in estimating the grain content, which with the yield map gives us the removal rates, pounds of P2O5 or K2O per acre. If we look at yields overall on the x-axis with the concentrations, what we saw from the Ohio State data, as we saw for the tri-states done by the Ohio State program, not really much here, not a surprise. You could argue these are more constrained. They're the same soil type. There's a couple of counties next to each other. Maybe at that localized scale, there is a correlation. And no, it's not a correlation statistically. Not much information either, though there's some variability explained. So expected, but good to look at that. If we look about the overspending is the term I'm using here, not over application. I think that's a good agronomic term in terms of need versus actual rates. Overspending again is the dollars spent versus what was needed for maintenance. If we look at the relationship of the costs with the removal delta, not really much here. This is that same field again. So we're seeing that we're spending a lot. We're overspending by 40 bucks per acre here. We're overspending, by the way, for the corn in every single grid point. They're all in the yellowish territory. We're overspending by 20 to 40 bucks per acre. For soybean, though, we're basically spending the right amount, so maybe a little bit more than what we should, as we were seeing for the Bureau County, Lee County, Henry County averages in those histograms a few slides back. Okay, if we look at interannual patterns, is this a strong annual effect? We see something shaking out here in terms of the overspending with the removal. So again, color is overspending. We're losing, or let's say we're spending 40 bucks per acre in this example here that we did not need to. And that tracks with the difference. This makes sense, right? There's more P2O5 in the handbook than what was measured, so there's more overspending. There's some correspondence. So we've got in this corner, there's more overspending, right? Across years than say in this corner over here. But then we've got these examples where we overspent in this corner one year, but not in this other corner. This is a corn on corn example. So it's corn both years. This is a good example of how it isn't that predictable by location in the field. So I'm running out of items on my list here. What could explain this? Is it interannual weather? Is it yield? Is it soil test? We've not looked at the genetics at the hybrids. We don't have that data. We're going to look into it, but this is also not the right place to look at hybrid data. Again, I would propose that we consider this as a multivariate outcome. So that's exactly the point of this slide, is that to enable the estimations to maximize ROI for VRT at any strategy, maintenance, drawdown, build, we need to understand and be able to estimate what's going on. This is not going to be an easy, simple correlation. It's going to be likely multivariate. But even if we can tighten the range of values that we can assume without grain sampling, If we can make some basic predictive models here based on hybrid, based on soil tests, even that might yield some improvements over current handbook values. So this then raises the question that I think we'll have time for some discussion on, and I'm curious to get your feedback, which is, should grain testing be part of how we manage our fertility? Should it be part of P&K programs? There's pros and cons here. So some pros. You're measuring the actual removal rates. This is it. This is the real number. And this is therefore useful to inform how you manage P&K applications, regardless of the strategy that you're undertaking, from drawdown to maintenance to build. It's also at the scale at which we manage, whether that's VRTing on a grid or whether it's the field. It enables VRT to be, I think, a lot more accurate. And as was brought up at the beginning of this, we have the infrastructure in commercial labs. If these labs run an ICP, they can, with a nitric acid digest, also run these. And if they're doing foliar analyses, it's the same method. So I think this is not saying, well, one, I'm not saying get rid of soil testing, but two, we're not saying to commercial labs, hey, maybe you need to add an entire new department for grain testing. It's more of a shifting the same approach, the same procedures for grain samples. I know that we send our samples to commercial labs from a few of the people on this call, and we get back great data when we check it with our own internal ICP measurements. So this can be done quite easily. Some cons here. How do you grain sample to get useful information? Do you have to do this on the field scale? We just saw good evidence that it varies so much within the field. Maybe it beats the handbook value, but maybe it's not worth the money to grain test. If we do grid sampling, what's the resolution? Is it a 2 acre grid? Is a 10 acre grid good enough? How do you actually grid sample a cornfield? I mean, it's like a yield estimate, but how do you do it for a soybean? Do you do 1 meter length? Do you do 10-foot length? These are the questions that I think would pose challenges, albeit not insurmountable, to see if this is valuable. Grain sampling is definitely labor intensive, not least because you have to walk a field. You can't just drive across it. I think that's the biggest issue with this. Moisture corrections, we got to be careful here. The data comes back from labs on a oven dry mass, 0% moisture. That would be important to communicate to crop advisors and farmers on, well, consider the percent moisture content here. And finally, like we do for any soil testing, as ALTA well knows, how do we ensure quality control? What's an acceptable variability on a standard measurement when it comes to grain P&K? I'd like to talk a little bit about why this matters beyond the economics, which I hope I've pointed out from this example in Bureau County can be appreciable, especially for phosphorus, especially for corn. This has to do with legacy phosphorus. Legacy phosphorus is basically a build approach that gets out of control. We build way too high, and that legacy P that's been built up over time can be a source of losses today. Here's an example of why this might matter. There's big implications for federal to state policy, and what ag and the role of ag in reducing nutrient losses. So this is a mass balance of phosphorus to Illinois croplands from 1945 through 2000. And if you're above that dotted white line, you're effectively in a positive balance. We did a lot of build in the 1960s and 70s in the state's croplands. Note how we're in a negative balance 1990 through today. I'll show you the through today part later. And if we add up this magnitude, we applied beyond removal roughly 200 pounds of P per acre, which is about 4.9 billion pounds of P. That's not P2O5. So that would be about 10 billion pounds of P2O5. That's a lot of DAP. Now, this is an average, but it gives you a sense of the magnitude. It's also not a huge increase compared to the geogenic. So compared to naturally occurring phosphorus, it's 5% more because we have 95 billion pounds of P in our soils naturally in the top 3 feet. So the bigger point here is that that's 203 pounds of P per acre, so 500 of P2O5 per acre average. Okay, so put that in your mind. And the other filing cabinet to open up, put in this. We have lost 35% P above our baseline in the last 5-year average report for Illinois, 17 through 21. we had to be going down by 35. We went up by 35, and that was in spite of the point sources, so the non-ag sector, decreasing by 25%. So the non-point source, which includes but is not the same as ag, it's mostly ag, it canceled out and then it added more P. But as we did from our group, these P balances through that same 5 year period, these two graphs, right, are the bounding years of that 5 year average. The state has been in a negative P balance of -7, roughly, -4 pounds of P per acre. So roughly 18 pounds of P2O5 to 10 pounds of P25 per acre in the negative. So this is a paradox, which means it's a bad explanation. It is not true that we saw this large increase because farmers were over applying P2O5. It's physically impossible from a mass balance. But if you remember that we had a 200 pound of P, so 500 pound of P2O5 per acre historical positive balance, that's precisely how legacy P might be impacting phosphorus losses today, even though farmers are doing, as you can see here, drawdown in most counties and thus as a state average. So this is important because we oftentimes are recommending that a best practice is drawdown if you're above 80 ppm melic, as an example from the Ohio states. Um, if your maintenance calculations, excuse me, if your removal calculation of P with grain harvest is off, then your calculations on what is a maintenance or drawdown may not be accurate. To put it differently, what you think is drawdown might be maintenance. And what might be maintenance is actually a build rate. So apart from wasting dollars on fertilizer, it's not exactly helping with water quality goals. This then is a different rationale, I think, for why this matters. Alrighty. To use this example that we saw at the very beginning, if we just do some basic math, if you are in these 10 percentile underfields, what it comes out to is that over 2 decades, we can build up a surplus of 222 pounds of P per acre. And that is basically the same number as the historical 203 pounds of P per acre of the state of Illinois from 1940, from 1960 through 1990. So this stuff seems like it doesn't matter. It's 10 pounds of P per acre plus or minus. Well, if you give that 2 decades, 20 harvests, maybe 10 applications on a 2 year cadence, you're already there with the historical average, apart from wasting money. So to revisit this idea, can grain testing improve the accuracy of applications? It can't but improve it. I don't see how it doesn't improve it. So then the next question to me is, does it help with the ROI? Where can I cut back to return to the motivating question of today's webinar? I think soil fertility, we often say, well, be careful, look at the soil tests. I would push back. Look at the soil test. But when you're doing your removal rates, if you're trying to do drawdown maintenance or build, you should, I think, consider the P and K offtakes. And for the labs that are part of the call here, I'd be very curious to hear if folks are doing this. I've heard some players in Illinois are doing grain testing because they're finding a lot of value for their clients in terms of savings. And the soil tests are doing just fine, and the yields are doing just fine, more importantly than the soil tests. So to summarize all this, I'll just leave this here. To summarize all this, I would just say that whether you're doing build, maintain, or drawdown, fundamental as an assumption, as a key calculation, all of those strategies is the removal rates. We use averages. That's great if you get nothing else. We have something else. It's called grain testing. Well, why not use it? We're losing money in the uncertainty in the distribution around the average. We've seen examples today where people were over applying P for corn, especially. There might be cases where there's actually mining going on, and the losses that are economic might be from lost bushels. So I'm not saying that we are always over applying. The example we saw was over application based on the handbook, but there's likely, it has to be true by distribution definition. There are likely places that are under applying, which might lead to mining of fertility that could be a problem in the short to medium term. So again, the economics, I think, are the motivation, though there are reasons to care about this for water quality. So with that, I'm going to stop. Happy to take any questions, have a bit of discussion in the time that we have.
Thanks, Andrew.
Sure.
Please, folks, if you got a question, bring it on out.
I have a question for the crowd. Is this crazy talk? I mean, is this either logistically from how do you grid sample grain to we tried this, it doesn't work, Andrew, to no one's going to want to do this. I'm just curious to get the temperature here on what you all think, those of you who are in the thick of it, boots on the ground with clients.
Andrew, this is Dustin Sawyer. I can speak to that a little bit. So, being an animal nutrition lab as well as a soil testing lab, we have a huge database of grain nutrient content regionally across the United States. And we have available actually on our website a nutrient removal calculator where you put in your yield, and we use our real data, and you can look at how it's changed year to year, how it changes across region. We have tried really hard to get our agronomy customers excited about this.
Hmm.
They just cannot care,
Hmm.
um, and it's really it, it's frustrating. The good thing has been we found that the numbers we're finding match published removal rates to a large degree. Where we really thought we were going to get people's attention is we have removal rates on all the micros as well, and people just don't know, like, micros are a crapshoot when it comes to soil fertility. We thought people would really like that. Um, we simply cannot get engagement on this, and I think it's just viewed as more work, and in the end, trying to get people to do more work, even though we know it's going to benefit them in the long run, it's just really difficult to do.
Thanks,
But
Dustin. This
I
is really, oh, sorry.
agree with your approach. Absolutely agree with it, and I'm super excited to see that you're out there preaching it.
Thanks, Dustin. And thanks for the perspective here. Do you think that the economics being shown might change those perceptions? Or do you think or was it just things were better a few years ago, price-wise, and maybe now people will listen? Or do you think that it's more of a cultural approach?
Uh, Scott Fleming just gave the 100%, but I'm not sure which one he was, and I was going to defer to him. I'm not sure which one he gave 100% to. Scott,
Andrew
you.
actually, I think, was hitting the nail on the head. With the tighter margin times, I think that's going to change how people look at this. I guess as long as I'm already unmuted, and Bob's had his hand up for 10 minutes.
Oh, sorry, Bob, I
Bob
missed
will
that.
always have his hand up. That's cool. Um,
Jeez.
but the way yield monitors work is they basically, at least John Deere's that I'm familiar with, have a slide gate and they grab a tiny sample of corn and put it against an EC monitor and check the grain. You know, I see this, into the future, maybe using the yield monitor or some portion of that to just grab our sample on the fly.
I agree. And one thing to add there, Scott, is that if that's based, there's infrared technology, right, that you use, like near is used for protein content for lots of grain. The same near infrared can also give you pretty good prediction of P and K content of really any element as a total. I could see a future where you fasten an infrared detector in that same little gate that you're describing for EC, and then you can get real time P and K contents and then real-time P and K maps. So
Yeah,
that's my own 2 cents on the technology. Seems like it's not too far away from making this a reality.
Andrew, this is Bob Miller. I got to tell you this. We go along in our scientific profession and we say, well, this is how, we're going to improve things for farmers, and this is the recommendations we're going to make, and we move forward, right? And then somebody like you comes along and says, I'm going to take a different perspective on this. And I think that's what we've missed. We haven't had somebody come into the market and say, well, look, what's the reality about these nutrient concentrations and the removal rates? I deal with a lot of clients,
Hmm.
that's all they use. They use the book value and the yield monitor, and that's what their fertility project is made for going forward. A couple comments I have. I think it's going to be a real challenge to pull samples in the field I mean, I'm sure there's a lot of labor involved, and how many corn ears does it take? And you brought up the point about soybeans. I can't even imagine that.
Yeah.
In terms of sensors, I'm not such a big fan of NIR, but there's other things on the markets coming online right now with libs, which I think would be even a sharper tool for
Mhm.
doing this. For the labs on the audience here who are planning to get in, maybe doing this, you know, getting a representative sample is going to be the challenge. I agree, nitric acid for P and K is easy. I got to tell you, it's a real challenge to process soybeans. I did this in my past history here, and you got to really know what you're doing because those oils in those soybean seeds, when you start to grind them up, I've seen a lot of labs that's, how should I say, turned peanut butter inside their grinders to grind up soybean seeds. I'll leave it at that.
You think you could maybe flash freeze it or just freeze it to
So,
try to?
so, so sidebar, gosh, guys, this takes me back 40 years. When I was at Texas A&M, we found that if you add 100 grams of dry ice to that soybean seed, and it was about, I think it was 50, 100 grams of soybean seed, you can prevent those oils from volatilizing and turning it into a sticky mess.
Hmm, interesting.
So,
Interesting.
no, listen, I applaud you because taking a fresh look at this from a different perspective, it's always important to have that because it kind of comes back to the point that, this is the reality. And I'll just say this, I think the soil test for cave personally is kind of worthless. And I would say this from this standpoint, the variety component and the weather component, I think are very significant factors here. Because if you have a situation where you start having water stress during grain fill and you change, the concentration of carbon in the system, right, going into those kernels, that's going to bias these numbers. And it would be interesting, maybe we'll have this across the Corn Belt this year, to see what the water stress during grain fill will have impact on those concentrations on removal. So,
Interesting. Well, thanks, Bob. That's encouraging to hear.
Anybody else?
Uh, Andrew, really appreciated your talk. Thanks for giving it. What
Thank
can
you.
we do as, commercial labs or people who have contact with growers? Like, what can we do to help get this word out? Because it seems extremely timely in terms of saving money and getting people dialed in with their actual removal rates.
Thanks, Caleb. I'm glad you asked because I do think that there's a little bit of responsibility, maybe more than a little, on the land grant recommendations. I mean, we've talked about the culture of what Dustin and Scott were saying, how like, you show people data and they don't really care sometimes, or they don't think it's worth it, is how I would interpret that. I I would argue that there's also a culture in the land grant, and the land grant comes up with these handbook values, right? These are the gold standard numbers. And I think we need to shy away from giving people single numbers and embrace more of the complexity. As Bob was saying, like this is what it looks like. I'm sorry, it sucks that there's a distribution, but you might want to consider that. So, to answer your question, Caleb, I think the land grants need to step up and pull back the curtain more on how we make recommendations. This extends, I think, to critical values, the soil case stuff that Bob is getting at. In the case of grain testing, I think, and what I'm trying to do in Illinois with colleagues is point this out and even make official land grant recommendations that you should really consider testing the grain, and that the handbook values are suggestions. Give people all the percentiles, not the number. I think that's a good step, 25th, 50th, 75th. And then in terms of how commercial ads can help, Luke and I are trying to drum up some support here to collaborate with testing labs like the ones that you all run. I'd be happy to talk more, and let me put my email in the chat. We're writing a few proposals right now. We'd love to partner with people that run commercial labs that have large clients that have interests. One thing that I've gotten as pushback is you looked at 23 fields over 2 years in 3 counties. Yeah, that's valid. And I think, are seeing an example where there were large savings because every field for corn was over for pea. There's going to be places, I'm sure, where they're way under, where we actually need to add more. So increasing the sample size and doing the economics, I think are two ways that we can get the word out. And if yourself and others, Caleb, have interest, we would love to talk with you all about how we could partner. NREC grants are coming up. We're thinking about putting a proposal on just this. And so having access to data sets that have been collected, anonymized, of course, being able to get programs going on grid sampling. These are two examples where we would definitely value partnering with people. The third area is hybrid trials. If we can pull grain samples of different hybrids at the same sites, same hybrid cross sites, and look at that genetic component, as Bob is hypothesizing, that would also be a value.
Hey,
You're
anything
welcome.
else? It's been very interesting, and very glad I recorded. I certainly hope people take the time and hear this, because this kind of sounds like something we're all going to be facing in the future.
Well, thanks
Anything else
again, Gary, for
for,
the chance. Oh,
yeah,
sorry.
anybody else for let everybody get on their way?
Yeah. Thank you, Andrew. I always love seeing your presentations and your unique approach to our situations.
Thanks, Dustin. It's good to be a heretic sometimes. I appreciate the feedback. Well, thanks again to everybody for their time. And again, for Gary for reaching out in the first place on this webinar. Thanks, Gary.
All right, guys. Everybody have a good week.
Take
And
care.
again, we recorded this. I'll get it up on our website probably in the next day or so. Everybody take care.